In this video, I'm going to go over 7.3 using similar right triangles. Now here is another video that I would recommend that you watch. This is not my video, but this will be helpful for you as well. So let's get some vocabulary behind us. So the altitude of a triangle is the vertical, so this word is vertical, segment from a vertex to the opposite side of a triangle. So let's just look at this triangle, and I want to do an altitude, so I'm going to change my color. So my altitude is going to be green. If you drop your altitude from the vertex, whoops, let me go back, do that again. Let's see if I can, okay, if I drop my altitude from the vertex to the side opposite it, having a hard time doing this. Gonna try that again. Just draw a straight line down. It hits at a right angle over here. That is called an altitude right there. Okay, so it goes from a vertex, which is the corner, to the side opposite of it. That's an altitude. So we're going to use this. Okay, a geometric mean is a type of an average, so just keep that in mind, because we're going to use that term. And then similar polygons we know from the past are shapes that have equal angles and their corresponding sides are in proportion. Okay, we just finished studying that not too long ago, so that should sound familiar. Okay, so now we're going to talk about a theorem. This is the altitude theorem. And the altitude theorem says, if the altitude, and we just did this in green above, is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. Okay, so I'm going to draw that for you, and we're going to do it more on the next page. So what if I have a right triangle that looks like this? So here's my right triangle. If I drop the altitude, so if I drop right here and I form another little triangle, another two little triangles, then the three triangles are going to be similar to each other. So what are the three triangles? Okay, so this is triangle 1, this is triangle 2, and then this entire big boy triangle is triangle 3. Those three triangles will be similar, and we're going to talk about that on the next page. Okay, so what you want to do is you want to look at these similarity statements. Okay, so this is what I have here. So this says triangle CBD. CBD is this triangle right here. So let me match it up with color. Okay, so this triangle right here, this blue one, is my CBD. So that's this one right here. Okay, the ABC is the big triangle, so I'm not going to color that in. The ACD is going to be this triangle right here. So this whole triangle right here is ACD. So what this is telling us is that the right triangle, which is right here, the right triangle is similar to the big triangle, and then the left triangle is similar to the big triangle. So therefore, what we're going to find is that the left triangle is also similar to the right triangle. So think of it this way. If A is to B, just like C is to B, okay, so then A is to C. So if you can relate A to B and C to B, you can relate A to C. That's what's going on here. And they have changed the orientation around for you so that you can see it. Okay, so let's look at this and see if we can figure this out. So let me erase for right now my coloring, because We've already made that point. So here is your big triangle. So I'm going to draw all three of these triangles with the same orientation. So here's my big guy. And what I see with my big guy is that C is my right angle. And then I have B here and A here. Okay, so look at the next triangle. I'm going to use the same orientation. Do you see how this A has to equal this A because it's the same angle right in here? So, and this is going to be C and D. And then let's do the next one. I'm going to change that orientation. So I'm going to flip this around the other way. This is the smaller of the two triangles that we just created. And this is B and this is C. So can you see that B right here has to be similar, or identical rather, to this B right here. So that's how I'm getting the similarity statements. Okay, so let me just go over a couple of more little things. Let's base our similarity statements now on what I have drawn. So let's look at triangle ABD, aka also known as the big boy. That is similar to, so look at this triangle right now. C is the right angle, so I'm going to make sure that C and D line up. And then A are the angles they have together, and the other angle in there is going to be C. Okay, so that's big to medium. That was big to medium. Okay, big to medium. Now let's do big to small. Okay, we're going to still call big ABC, keep the same letters. Now, look what we have. The A does not have an angle in common that I know of right away to the other triangle, to the small triangle. So this is small right here. So let's line up the angles we do know that are the same. Okay, C has to be the same as D, because they're both right angles. And then the B angle has to equal the other B angle. Okay, what's the other letter in that small triangle? C. Okay, so that is big to small. How about doing medium to small? Since the bigs had the same order of letters, we can then use the same order we have there. ACD is going to be similar to CBD. Okay, and so what I know is that A is going to be the same as C in the other triangle. So this A, let's see if I can get this to work out for me. This A will be the same size as this C here. So red is to red. And then look at the other letters. So there's red is to red. And then the C in the medium lines up with the B in the small. So let's make them a different color. C in the medium lines up with B in the small. So C and B. And then the last one is the easiest because they're both right angles. So then this lines up with this. That goes with that. And that's how I know my statement is correct. Okay? So that's an important page. You may want to stop the video, rewind it, and listen to that again. Because the next thing we're going to do is work with the geometric means. Okay, so let's do that on the next page. Okay, so now in this page, we're going to talk about the geometric mean theorem that deals with the altitude. So this is your theorem. In a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. The length of the altitude is the geometric mean of the lengths of the two segments. Okay, so what does that mean? Do you remember when we were doing similar triangles and we set up these kind of proportions? Okay, so I want to define things for you. Okay, this and this are called the extremes. Okay, they're both called extremes. It's just what that part of the fraction's called. And then this and this are called the means. Okay, so let's get ourselves a right triangle. And I'm going to put some numbers on it. This is the same triangle we just talked about. We had a right triangle, remember? And then we dropped the altitude and we formed two similar right triangles. So instead of labeling this with letters in the corners, I'm going to instead label it Y, X, and maybe I'll call this A for altitude, and then 15 and 4. Okay, so this is what you can do. You can set up a proportion, and in a right triangle, the altitude from the right angle to the hypotenuse, that is A. It is the geometric mean, therefore you put A here and A here, that's the geometric mean spot, between, of the lengths of the two segments. So the two segments formed are 15 and 4. So 15 and 4. So you're basically saying 15 is to the altitude, just like the altitude is to 4. So you're making this comparison. But for our purposes right now, I'm going to view this as a multiplication problem that we can solve. So when we do that, we're going to say A times A, which is A squared, equals 4 times 15. And 4 times 15 is 60. So therefore A equals radical 60. And what does that break down into? Let's see. This is, so 60 is 2 times 30. So I can say 2 times 30, which is 2 times 2 times 15, which is 2 times 2 times 5 times 3. Pull out the double pairs as a single. The 2 goes in front, and the 5 times 3 stays inside, and therefore A equals 2 root 15. And that's our altitude. Okay? So this is the geometric mean example. And the key thing to remember is that the geometric means go low spot, and high spot. Low, high. Okay, so that's how they go. And then what did I put on the other part? This is a piece of the hypotenuse. And this is a piece of the hypotenuse. Okay, so that's what I want you to know for this page. Let's go to the next one and we'll talk about another type of geometric mean. Okay, so this is geometric mean leg theorem. So I'm going to change my colors just so it looks different to your eye. In a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. The length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segments of the hypotenuse that is adjacent to the leg. Okay, so let's figure this out. So I'm going to draw another one of those right triangles in the same orientation just to be consistent. I drop the altitude. I form two other triangles, both of which are similar to each other and similar to the large triangle. And let's go ahead and maybe for this one, we'll just keep it in our letters. Okay, so I'm going to label this. We're going to set this up a little bit differently, just so you can see the theory behind it. And what this tells us is I can get two geometric means. So the first one, take the length of the leg. So this is a leg. This is leg 1. This is leg 2. So leg 1 is the geometric mean. So put it in the geometric mean spot between the piece of the hypotenuse closest to that leg, which is AD, and the entire hypotenuse, which is AB. So that's our first one. Let's do the second one. So we'll do this in pink. So the second one tells us that the second leg, which is leg 2, so let me call this leg 2 and we'll do it in pink. Leg 2 is the geometric mean. So pop it, oh sorry, I don't want to write that. Pop it in the geometric mean spot, and it is piece CB, and CB is the geometric mean between the piece of the hypotenuse closest to or adjacent to the leg 2, which is DB, and the entire hypotenuse, which is AB. Okay, those are our two equations that we can get. Now, if we have values, we can plug them in and we will be able to solve for the different pieces that are missing. Okay, so two important geometric means. One was the altitude and the other are the legs. Okay, so let's keep going because I have more practice for us. So here we're going to actually use the geometric mean. And it talks about finding the value of y. And look, y is a leg. So a leg. So what do we know? We know this. We know the leg is the geometric mean between the piece of the hypotenuse closest to it and the whole hypotenuse. Since we have numbers now, we can actually put numbers in and solve for some things. I don't know what the leg value is, but I do know the piece of the hypotenuse closest to that leg, and it's adjacent to it, is the 3, and the entire hypotenuse is the 9. So look what I'm getting. Y squared equals 27. So y equals radical 27. Y equals 9 times 3, which is also 3 times 3 times 3. That comes out as a single, and we're left with 3 root 3. So what do I find? I know that y equals 3 root 3. You should be writing all this stuff down in your notes. Okay, let's go to the next page and do this other practice. You just make sure it's the same thing, yes. Okay, so we're going to do this practice. It says find the value of k. Oh, look. K is also, what? A leg. So what do I know? I know leg, goes in the geometric mean spot, piece of the hypotenuse closest to the leg, and the entire hypotenuse. So I can now replace the word leg. So I'm going to change leg so that now you know that that's what the k is. So what am I getting? K squared equals 20. K equals radical 20. K equals 4 times 5. K equals 2 times 2 times 5. K equals 2 root 5. Okay, I can have a value for k based on the geometric means of the legs. Okay, so look what I have here. They don't tell us what they want us to look at, so why don't we set them all up? So we'll do altitude first. So what do I know about the altitude? Here's the altitude. Okay, so that's going to go in the altitudes in the geometric mean spot, which is right here, dB, dB, and then it's going to be AB with BC, because it's the two pieces of the hypotenuse. So this is the altitude. Okay, then let's do a leg. So here's a leg right here. Put your leg in your geometric mean spot. This is AD, AD. It's the geometric mean between the piece of the hypotenuse adjacent to that AD and the entire hypotenuse. So this is a leg. Let's do a third leg. Or a third formula, a second leg. Okay, so that's the purple. So that's a leg. It goes in the geometric means position, DC, DC, and then I know that's the geometric mean between the piece of the hypotenuse closest to the leg, which is BC, and the entire hypotenuse. So that's the second leg one. So these are the three geometric means that we can get going. So now your job is to look and see if you can match one up. So I'm going to pause this for right now while you do that. Okay, so look what I indicated. I found that AB over DB equals DB over BC matches that one. That's the only one that matches the proportions that I have delineated. Okay, so hopefully you got C also as being the one to select. Okay, so let's keep going because I want to do a couple of these homework problems. Okay, so here it says identify the three similar right triangles in the given diagram, draw and label each separately, and write a similarity statement connecting all three triangles. Okay, so we're going to do number one together, and then you'll be able to do number two. So what I'm going to do is I'm going to draw the big triangle in this orientation. Okay, so that big triangle, this is going to be B, this is going to be A, and this is going to be C. So you see I just flipped it over? Then grab the medium sides. Maybe I'll change colors as I do that. So the big's going to be the green. And the purple will be the medium side. That's probably the easiest to draw because the orientation is exactly what you're seeing. And then we'll do the last one in a darker blue. You've got to flip that around. So this is a little bit challenging, but probably the most challenging one is the big one. Okay, so I know that this is a right angle, this is my C, and this is my B. Okay, so what I'm going to do right now is I'm going to compare the big, so I'm going to label these. This is going to be small. Okay, so I'm going to continue labeling things here. So this will be the medium size right here, and then this is going to be the big guy. Okay, so he's the big triangle. Okay, so I want to get my similarity statements going, but before I do that, what I'm going to do is get the similarity, label angles that are similar between the big and the medium and between the big and the small. Okay, so that's my main thing. So what I see right away is that this is similar to this. It has to be identical, right? So those triangles are similar by virtue of those angles being the same. And then look at the big and the medium. Don't they both share A? So I'm going to give A a single mark, and I'm going to give A a single mark there. So I can now say that the similarity between the big and the medium is as follows. So why don't I start, I'm just going to call it ABC is similar to ADB. Okay, so this is big and this is medium. Okay, so now compare the big with the small in terms of the angles that we know are the same. So what we know is that this is a right angle, so this and this angle are both right. And then look at the C angle. The C angle in the big is the same measurement, because it's the same angle as the C angle, as the C angle in the small. So now based on that, let's write a similarity statement between the big and the small. So we'll change colors for that. So that's going to be ABC, that's the big again, is similar to, okay, so the A is the not similar angle, so that not identical angle. So that's B, and then the B goes with the right angle, so that goes with D, and the C are the same. So there are the two similarity statements that we need to base everything off of. So this is big to small. So now when you want to do medium to small, go with ADB and BDC. Just write it in, use the letters that you see here and here, And you then have the third statement. So you have one statement between big and medium, one between big and small, and then the last one between medium and small. Okay, so you should be able to do that now with the second homework problem there. Okay, moving on to this next piece, what I wanted to do was to use the geometric mean to find missing values. So we're going to do 1, and I'm going to do, maybe we'll do 3. Okay, so this number 1 deals with the altitude. So this is the altitude mean, geometric mean statement. So what the altitude geometric mean tells us is put the geometric mean value of x and x, those are the altitude values, in the geometric mean's location. And then each piece of the hypotenuse goes there and there. Okay, so we have x squared, we're looking for x, equals 9 times 16. And the product of 9 times 9 and 16 is going to be 144. And you should know that that is 12 squared. So x is 12 is our answer there using the geometric mean. Okay, so I'm going to change my color. And this is the leg, the geometric mean using the leg. So look what we're going to do. Set these two equal. Put the leg value in the spot where the geometric mean goes, which is always going to be low-high. And then the way it works is you take the piece that's tangent or that's adjacent to the x side, which is the 36, and the entire hypotenuse, which is 100. So do your cross products. X squared equals 3600. So x is going to be 60 because radical 3600 is going to be 36 times 100. That's 6 times 6 and 10 times 10. So you bring out each of those pairs as singles, and that's how I'm getting 6 times 10 or 60. Okay, so I've done both geometric means. So you have examples of all kinds of stuff to be able to do this homework. So definitely go back and listen to this, but also make sure that you have your notes written down accurately, and I would reread your notes so that you are really internalizing this information.